Unraveling the symbiotic dance between algorithms and data structures in the intricate world of computer science, algorithms and data structures form an inseparable partnership that shapes how we solve problems efficiently. Understanding their relationship is crucial for any developer aiming to build robust and high-performing applications. This exploration delves beyond surface-level knowledge to uncover how these two fundamental pillars interact, influence each other, and determine computational efficiency in real-world scenarios. The foundational interplay at its core, an algorithm defines the steps required to accomplish a task, while a data structure provides the framework for organizing information. Their synergy determines how effectively solutions can be implemented and executed. Choosing between different sorting algorithms, for example, often depends on the underlying data structure being used. A linked list might favor certain operations over arrays due to memory considerations. The performance characteristics of both elements must be carefully balanced during system design decisions. An optimal solution requires evaluating time complexity against space requirements based on expected input sizes. When designing complex systems, developers must anticipate future scalability needs by selecting appropriate combinations of algorithms and data structures from the outset. Data structure influence on algorithm selection. Many standard algorithms are specifically designed to work optimally with particular data structures. This dependency creates tight coupling between implementation choices and runtime behavior. For instance, breadth-first search performs exceptionally well with queues because of the FIFO principle inherent in queue implementations. Changing the underlying data structure could significantly impact performance metrics. Tree-based structures enable efficient searching through hierarchical organization principles. Hash tables offer constant time lookup capabilities when properly sized. Graphs require specialized traversal algorithms that respect adjacency relationships. The choice of data structure becomes even more critical as datasets grow larger. Proper selection ensures maintainability and avoids potential bottlenecks. Modern software development increasingly emphasizes understanding these dependencies to create scalable, maintainable codebases that adapt easily to changing requirements. Algorithmic complexity and structural constraints. Analyzing time and space complexity reveals deeper connections between algorithms and their associated data structures. Big O notation helps quantify these interactions mathematically. Insertion sort demonstrates linear time complexity with arrays but degrades rapidly with unsorted inputs. In contrast, heap sort maintains logarithmic bounds regardless of initial ordering due to heap properties. Different operations exhibit varying efficiencies depending on the chosen structure. Array access is typically O(1), while insertion into a sorted array may require O(n) operations. Understanding these trade-offs enables programmers to make informed decisions that balance execution speed with memory usage according to application-specific constraints. Symmetry in design philosophy. The mutual reinforcement between algorithms and data structures extends beyond mere functionality to encompass broader design philosophies in software engineering. Object-oriented principles often manifest through encapsulation of both algorithm logic and structural management within cohesive units. This approach enhances modularity and reusability across projects. Functional programming paradigms leverage immutable data structures to ensure predictable outcomes when applying transformation algorithms. Pure functions benefit greatly from persistent data structures where modifications don't alter existing state but instead produce new versions through copy-on-write mechanisms. This philosophical alignment continues evolving alongside advances in parallel computing and distributed systems architecture. Emerging trends and paradigm shifts. Recent advancements in machine learning have introduced novel challenges requiring specialized algorithms and innovative data structures to manage vast amounts of information effectively. Neural network architectures demand highly optimized matrix operations that necessitate special-purpose hardware acceleration techniques paired with tailored storage formats. NoSQL databases exemplify modern approaches where flexible schema designs accommodate dynamic querying patterns without sacrificing performance guarantees. Blockchain technology relies heavily on cryptographic hashing algorithms combined with linked list-like structures to ensure security and immutability at scale. Cross-disciplinary innovations continue reshaping traditional boundaries between algorithm design and data organization strategies. Performance optimization strategies profiling tools provide essential insights into identifying performance bottlenecks caused by inefficient combinations of algorithms and data structures. Cache-conscious optimizations become particularly relevant when working with large datasets stored in memory. Aligning data layouts with CPU cache line sizes reduces unnecessary page faults. Lazy evaluation techniques allow postponement of expensive computations until absolutely necessary, improving responsiveness in interactive applications. Concurrency models introduce additional layers of complexity by adding synchronization overhead that must be factored into overall efficiency calculations. These optimization paths illustrate the ongoing need for careful analysis before finalizing implementation details. Educational implications and learning pathways. Mastery of both domains requires structured progression through foundational theories, practical implementations, and advanced analytical skills. Beginner level, focus on basic sorting/searching techniques using simple structures like arrays and lists. Intermediate level, explore tree traversals, graph algorithms, and hash table implementations. Advanced level, study amortized analysis, randomized algorithms, and concurrency control mechanisms. This layered approach enables gradual skill acquisition suitable for learners with diverse backgrounds entering the field. Future directions and research frontiers. Ongoing research explores hybrid models combining traditional methods with emerging technologies like quantum computing and neuromorphic engineering. Quantum algorithms demonstrate remarkable promise in solving NP-hard problems exponentially faster than classical counterparts when applicable. Neuromorphic processors challenge conventional wisdom regarding sequential processing limitations through biological inspiration. Cross-disciplinary collaboration remains vital as researchers seek breakthroughs that transcend individual domain expertise. Continued investment in both theoretical foundations and experimental validation will shape tomorrow's technological landscape. Conclusion: the symbiosis between algorithms and data structures forms the bedrock of effective problem-solving in computer science and software engineering disciplines. To achieve mastery, practitioners must cultivate deep understanding of how these components complement each other rather than treating them as independent entities.